All right, let's pick back up and talk about how to graph logarithmic functions. So this is y is equal to log base 3 of x. Now, on the first portion of this video, we talked about how logarithms and exponents are inverses. They're opposites of one another. And we also learned two methods of switching back and forth between logarithm form and exponential form. And that's what we're going to use to help us graph logarithmic functions. So I'm going to go ahead and write this out again. It was y is equal to log base 3 of x. Now, when you look at that, you might be wondering, well, Mr. Cottle, how am I going to make a table for that? I'm still confused on logarithms, and that's normal. And that's why we have those different methods to switch things back to a form we're more comfortable with. So what we're about to do is we're about to do a loop and swoop here, which is where you take the base, raise it to that power, and set it equal to the final portion. So really what we're going to make a table for is 3 to the y is equal to x. Now, since logarithms and exponents are inverses, which is the opposite, what we're going to do is not fill in the x column, but rather fill in the y column. Now, negative 2 to 2 is typically what we place in for x, but we're working with a logarithm that we've switched around forms into exponential, but notice that we're now solving for x and that our input is y. So we're going to be working backwards essentially. For all the tables you've pretty much ever created, you've had the x values and you plugged them in to find the y. Logarithms is just doing the opposite. Once it's in the proper form, we'll plug in the y coordinates to find the x. So this x coordinate is going to come from 3 to the negative 2, 3 to the negative 1, 3 to the 0, 3 to the first, 3 squared. 3 squared is 9. This is 3. Anything to the 0 power is 1. 3 to the negative 1 power is 1/3. 3 to the negative 2nd power is 1/9. So we're now going to have enough data to get this graphed. And as you might remember from the first portion's video, this one has an asymptote. The logarithms have an asymptote, but it's not on the x-axis like exponential functions, but rather it's on the y-axis because they're inverses. So here's what it's going to look like when I graph this. 1/9 negative 2. 1/9 is barely to the right of 0. So it's right there. And then it's 1/3 negative 1. So about right there. And then it was 1, 0, 3, 1, and 9, 2. Now remember here that it does have an asymptote, and you can kind of see how these points are going to develop one, because they'll come in and curve down and get right here on this y-axis. And that's an asymptote. It'll never actually reach that 0, right? Because if you think about extending this table, this next value here would be 1/27, then a 1/81. It would never quite reach 0, which is why we'd never touch that y-axis. All right. So that's how you can graph logarithms. You use loop and swoop to switch it into exponential form, and then you make a table. But what's interesting about it is that you are selecting the y coordinates. That way you can find the x, which is opposite of what you've always done, but that's because logarithms are the opposites of exponential functions. We're going to bring back the transformations, because transformations will be very helpful when it comes time to graph logarithms. We didn't really use the transformations on exponential graphs because they're a little bit trickier to do because of some of the different implications of there being h values up in the exponent. You could have used them. I just had us use a table method essentially to create those. But you'll remember these shifts as always, same as always. If we have some type of h value, right? H moves us horizontal, but you have to remember that it's going to do the opposite of what you would expect. as far as it goes in terms of moving left or right. If we have a k value on the outside of the parentheses, that shifts us up or down vertically. And then we have an a value out front, if there's something out in front. And that's the one that it's a stretch factor to where it makes it grow more quickly if a is greater than 1. It's what's called a compression if a is in between 0 and 1. It'll slow down how fast it's growing. And then finally, if you had a negative out in front, that is an x-axis reflection. It would turn it upside down. Those shifts allow us to continue to graph logarithm functions to where we could do something like this. Say I now wanted us to graph y is equal to still log base 3, but this time x minus 1 plus 3. Right? And the reason I'm keeping it the same as this is, and I'm just making a few changes, is so that we can see how shifts work. What this minus 1, it makes me want to go to the left one, but that really means I need to move to the right one. And this k value means I need to move everything up 3. So if I go here to my graph, and I move all those points to the right 1 and up 3, we'll get this as our graph. So let's start. I'm going to move this first one to the right 1 and then up 3. So he'd now go right there. I'm going to move this next one, right 1, up 3. I'm going to move this next one, right 1, up 3. This one, right 1, up 3. And then the final one, right 1, up 3. Now, since we had moved to the right one, our new asymptote's going to be not on the y-axis, but at x is equal to 1. Because if the asymptote naturally occurs, usually on the y-axis, and it got moved to the right one, now it would be 1 to the right, where that asymptote is. But it's the same graph, except now shifted right 1 and up 3. And that's how you would go about graphing something like y is equal to log base 3 of x minus 1 plus 3. You'd first complete this process to graph the parent function, which we did in blue, and then you would simply apply the shifts, which is in this case going to the right 1 and up 3.